Hello, my name is Hans Burgerhoff and I work as a statistician in the UMCG. This video is part of a series of videos about medical statistics. In this video, I would like to tell you something about probability theory to understand what's going on in statistics. First of all, what is the difference between a probabilistic problem and a statistical problem? A typical problem from probability theory would be, we have a box, 10 balls. 6 of them are blue and the other 4 are red. So we know the content of the box. Randomly, we take out one of the balls. What is the probability that the color of this ball is red? In statistics, it's in fact the other way around. We do not know the content of the box. For example, we have a certain population and we would like to know the prevalence of a specific disease. We take out randomly a sample of the balls. From the sample we can see 3 out of 10 are red. What does this tell me about the proportion red balls in the box? What does the sample give me for information about the prevalence of the disease in the total population? To understand statistics, we need to have knowledge about probabilities. To get a feeling about probabilities, we will start with a definition of probability given by Pierre-Simon Laplace around 1800. He defined the probability to a certain event A as the number of outcomes in favor of A divided by the number of possible outcomes. To give you a simple example, if I throw a dice, I wonder what is the probability that the side with 5 dots will face up. The answer will be 1 out of 6. The probability that the number of dots will be even, well, there are 3 numbers of outcomes in favor of A, 2, 4, and 6, out of the number of possible outcomes. So the probability will be 3 divided by 6.5. Next question is, we know a woman is pregnant with 1 child. What is the probability that the baby will be a boy? Before answering this question, I will ask you a new question. I have a bag, and in the bag will be 10 apples. 9 of them are red, and only 1 is green. Now I take out randomly one of the apples. What is the probability that the apple will be green? Now you can say there are 10 apples in the sack, so the probability to have the green one is 1 divided by 10. But you can also argue there are only 2 colors, and the probability I take the green color is 1 divided by 2. Something is going wrong here. It's not possible that both answers are correct. What's going on? Well, I didn't tell you the complete definition of Laplace. We should add to the formula if all possible outcomes are equally likely. And this was not the case in the colors. There were 2 colors, but they are not equally likely. All 10 apples are equally likely. So you were right in thinking me taking the green apple has a probability of 1 divided by 10. In the example of the dice, we assumed all 6 sides were equally likely. So we assumed to have an unbiased dice. Now back to the pregnant lady. The probability of having a boy, well, there are only 2 possible outcomes. Can we conclude that the probability of a boy is 0.5? By looking at the formula of Laplace, then we assume all possible outcomes, boy and girl, are equally likely. So we assume the probability of a boy is 0.5, and then we calculate the probability as being 0.5. We have to conclude we cannot use Laplace formula in all cases. There is also another definition of probability we can use in all cases, the empirical definition. The probability on a certain event A is defined as the limit for n going to infinity for the number in favor of A observed divided by the total number of experiments. So we just observed thousands of babies and we simply look at the relative frequency of boys. If n becomes very large, this relative frequency or proportion will stabilize. In the Netherlands, the proportion of boys is around 0.52. In a lot of situations, for example, if we randomize and all objects have the same probability, we still can use Laplace's classical definition. Now we have some feeling for probabilities, we will have a look at two common probability distributions, the binomial distribution and the normal distribution, also known as the Gaussian distribution. In chapter 15 of Kirkwood and Stirner, there is a following example of a binomial distribution. A man and a woman both have sickle cell trait. They are heterozygous and have both probability 0.5 to pass the S gene to their children, independent of each other. So for a single child of these parents, the probability to have the disease is the probability of both father and mother passing the S equals the probability that the father passes S multiplied with the probability that the mother passes S. So 0.5 times 0.5 is 0.25 if the events passing on a gene are independent of each other. Here we use the product formula of probabilities. Now these parents have 4 children. What is the probability that exactly one of them has sickle cell disease? Let's see what will happen in this example. We assume all children have the same probability of the disease, independent of each other. The probability that the first child will have the disease is 0.25. The probability that the child will not be diseased is 0.75. The probability that none of the 4 children will have the disease is only one branch of this tree. The first non-diseased, the second non-diseased, the third and the fourth. None of them are diseased. The probability that this will happen is 0.75 to the power 4. Only one branch. If you want to know the probability that exactly one child has the disease and the other 3 have not, then several things can happen. The first child can have the disease, but the other 3 are not diseased. The probability that this will happen is 0.25 times 0.75 to the power 3. But this is not the only branch that will lead to the outcome exactly one child diseased. It's also possible that the first child is not diseased, the second is diseased, and the third and the fourth are not diseased. It's also possible of non-disease, non-disease, diseased child, non-diseased child, or the 3 childs which are born first are not diseased and only the youngest child is diseased. So we see 4 possible branches all leading to the same answer, exactly one child diseased. All those branches have the same probabilities. So the total probability to have one child, exactly one child with a disease, is 4 times 0.25 times 0.75 to the power 3. Now, in general, for a binomial problem, we have n independent observations of a binary variable, with outcomes success or failure, all with the same probability of success, pi. The probability of observing exactly these successes in those n observations, all independent of each other, can be calculated by the formula n over d pi to the power d times 1 minus pi to the power n minus d. N over d can be calculated as n factorial divided by the product of n minus d factorial times d factorial. This is called the combinations of d out of n. N factorial can be calculated with the formula n times n minus 1, etc. back to 1. For more information about this formula, please see chapter 15 of Kirkwood and Stern. A binomial distribution is an example of a probability distribution of a discrete outcome variable. A well-known distribution of a continuous variable is the normal distribution, also known as the Gaussian distribution. These distributions are often observed for empirical data on heights, weights, blood pressures, and so on, but also play an important role in statistical theory. I will tell you more about that at the end of the video. Normal distributions all have the same shape and the same features. Within the range of one standard deviation below the mean and one standard deviation above the mean, there is almost 68% of the distribution. Within the range of 2 standard deviations below and 2 standard deviations above the mean, there is almost 95% of the distribution. And within the range of 3 to the left and 3 standard deviations to the right, we have more than 99% of the distribution. Let's have a look at a simple example. In a certain population, the IQ is normally distributed with mean 100 and standard deviation 15. What part of the population has an IQ larger than 130? Well, the standard deviation is 15, and the difference between 130 and 100 is exactly 2 standard deviations. So we know that 95% of the population is between 70 and 130. So the remaining 5% is in the tails. The distribution is symmetric, so almost 2.5% will have an IQ larger than 130. But what part will have an IQ larger than, for example, 137.5? We cannot see this directly from the population. We need a table to have the exact answer. We need a table of the standard normal distribution. Now, the standard normal distribution, also called the Z distribution, is a normal distribution with mean 0 and standard deviation equal to 1. There is a table of this distribution in the book written by Kirkwood and Stern, and we can use this table to answer questions like, what is the probability to find a Z value larger than 0.56? So in this case we are interested in the area on the right hand side of the Z value 0.56. To answer the question, what is the probability to find a Z value smaller than 0.31, we are interested in the area on the left hand side of the Z value 0.31. On page 471 in the book of Kirkwood and Stern, we can find the answer to our questions. In the table, the area on the right hand side of the Z values are tabulated. If you want to know the area on the right hand side of the Z value 0.56, we look at the first decimal of Z in the first column, and we take the column with the given second decimal. and we will find the area as being 0.2877, so almost 29%. For the probability that Z is smaller than 0.31, we need to look at the first decimal 3 and the second decimal 1, and we will find the tabulated value as being 0.3783. This is the area on the right hand side. So we have to subtract this value from 1 to find the value 0.6217 on the left hand side. In real-life problems, we will work with normal distributions with all kinds of means and standard deviations. But we only have the single table of the standard normal distribution. So we have to translate our real-life problem to a problem of a standard normal distribution. For example, we have a population of individuals with normally distributed blood pressures, with mean 110 mm mercury and standard deviation 12 mm mercury. If we take out randomly one individual from the population, what is the probability that this individual will have a blood pressure larger than 160 mm? We don't have a table of this normal distribution. We start by subtracting the population mean, 110, from this problem. In fact, we shift the distribution to a distribution with mean 0. The area we are interested in the new graph is on the right hand side of 6. The second step will be to change the standard deviation of 12 to a standard deviation of 1 by dividing all values by the given standard deviation of 12. You see, we are still interested in the same part of the distribution. In fact, in all three graphs, it's the area on the right hand side of half a standard deviation above the mean. This process is called standardization, and it enables us to use the table of the standard normal distribution. The probability of finding an individual with a blood pressure larger than 116 from the given population is equal to finding a Z value larger than 0.5. From the table in the book, we can see that this value is around 0.31 or 31%. Maybe that some of you used graphical calculators in high school mathematics. You can use the function normal CDF, the normal cumulative distribution function, and you will find the area on the left hand side. In statistics, we are often interested in means of observations instead of individual observations. Let's first consider a question about one individual. We have a given population with normally distributed blood pressures with mean 130 and standard deviation 10. If we take out randomly one individual from the population, what will be the probability that this individual has a blood pressure smaller than 128 mm mercury? We already saw how to solve this problem by standardization. The probability that x is smaller than 128 is the probability that Z will be smaller than 128 minus 130 divided by 10. It's the probability to find a Z value smaller than minus 0.2. And from the table we find the value 0.4207. Now question 2 addresses a mean blood pressure of 25 randomly chosen individuals. Will the answer be the same? Will the answer be 42%? To calculate this, we need the standard deviation of a sample mean. And I'll show you on the next slide how it works. I simulated from a known population with a known mean and a known standard deviation some samples. I took a random sample of 25 observations and I calculated the sample mean. The sample mean for this first sample was 127 0.4. Then I did it again. Again 25 observations, and I calculated the mean, 130.3. And I did this again and again and again. The last sample, also 25 observations, had a sample mean of 129.6. Now I was interested in the standard deviation of those sample means. I calculated it, and it was around 2.15. Much smaller than the standard deviation of the individual observations. Mathematical theory shows that the standard deviation of sample means equals the standard deviation of the population divided by the square root of n, in which n is the sample size. This standard deviation of the mean is also known as the standard error. For standardization of a sample mean, we use the formula z equals the sample mean minus the population mean divided by the standard error. Standard error given as sigma divided by the square root of n. To return to question 2, what is the probability that the mean blood pressure of 25 randomly chosen individuals will be smaller than 128 millimeters mercury? We standardize this problem by subtracting the population mean and dividing by 10 divided by the square root of 25, which is 2, so we get a z value of minus 2 divided by 2, which is minus 1. From the table we can find this is a probability of 0.1587, so almost 16%. To end this video, I will show you why the normal distribution plays such an important role in statistics. Here is some information about sample means. If we take a random sample, we expect the sample mean to be close to the population mean. If we were to take several samples and we calculate the mean of all sample means, then we expect this mean to be even closer to the population mean. I guess you can agree with that. If we look at the variation between the sample means and calculate the standard deviation of these sample means, this will be close to sigma divided by the square root of n. I can see you smile, because you already knew it. If we had originally a normal distribution we sampled from, the distribution of sample means is also normal. I think you're willing to believe that. But also, if the population distribution is not normal, the distribution of the sample means is almost normal for large n. This is called the central limit theorem. And I can imagine you're a bit surprised by that. I will show you an example first. I have this single unbiased dice, which I will throw 120 times. The possible outcomes are 1 to 6. What do you expect of the frequency distribution of these 6 outcomes? I throw 120 times. So we expect the frequency around 120 divided by 6 is 20 for each possible outcome. The bar graph with the results shows, as we expected, a uniform distribution. SPSS tells me that the mean of all those observations was 3.45, close to the 3.5 we would expect. Now I will throw 9 dice at the same time, and I calculate the mean of the number of dots of the 9 dice. What do we expect to see from the sample means if I repeat this 120 times? For this first example, the mean was 3.45 5, 6. But what will the total distribution look like of all those sample means? Well, here it is. We don't see any uniform distribution anymore. It tends to be a normal distribution. We don't see any 6s anymore. How come? Well, the probability of finding a mean of 6 dots is the probability of finding 9 times a 6. And this probability is very, very small. It didn't happen in the 120 trials I did. So, what's so important from this? A consequence of the central limit theorem is, although some variables do not come from a normal distribution, for large samples, means of these variables can have a normal distribution, and we can use the theory and the table of the normal distribution for these sample means. Well, so much for probability theory. Please make the exercises, check your answers, and continue with video 4 about confidence intervals. Good luck!